Okay, so let us start our third class. Recall that in the first class we saw the Riemann sphere. We studied some basic properties of its three models, its three realizations. And in the second class we saw the definition and some basic examples of Möbius transformations. We defined a Möbius transformation of the complex projective line to be any function from P1C to itself induced by a C-linear bijective map from C squared to itself. In other words, we defined Möbius transformations to be the shadows at the level of P1C of the linear maps from C squared to itself. Then we saw that some obvious functions are Möbius transformations of C bar, of the extended complex plane. And then we exploited the simplicity or the simple-mindedness in how these functions are defined to make a basic analysis of their geometric behavior, with the promise that later on this geometric behavior that we were able to do for this obvious or very simple-minded Möbius transformations will be pulled to an analysis of the geometric behavior of any Möbius transformation. Right? So that will be the logic. But for today we are going to say some words about the group structure of Möbius transformations, of which we already said some things already. We are going to say a few more things. We are going to establish the famous simple transitivity on triples of distinct points of C bar. And finally, we are going to see that any Möbius transformation sends circles in C bar to circles in C bar. A fact that, by the way, it does not quite follow from the simple transitivity. And it's a fun game that I encourage you to play to try and prove the fact that any Möbius transformation sends circles to circles using only the simple transitivity on triples. So it's a fun game to try to show that this implies this. Okay, and then from the fact that circles go to circles, we are going to show that also disks go to disks. Disks in C bar go to disks in C bar under any given Möbius transformation. And that will be today's class. Okay, so let us start with how Möbius transformations form a group. So remember that I actually solved exercise 11 for you, proving that that the Möbius transformations of the complex projective line form a subgroup of the group of self-homeomorphisms of the complex projective line. So this we already know, that Möbius transformations of P1 form a group on their composition. I'm going to denote this group by this, Möb plus of P1C. The plus comes from the fact that Möbius transformations preserve the orientation, but for the moment I'm not going to say more about that. Okay, and then one can immediately deduce that the group of Möbius, the set of Möbius transformations of C bar also forms a group, and that is simply because of the relation that any Möbius transformation associated to a matrix keeps with the Möbius transformations associated to linear maps. Namely, if you give me a 2 by 2 invertible complex matrix, and give me any ordered basis, then the relation between the Möbius transformation of C bar associated to A and the Möbius transformation of P1C associated to FA is this one. This one is the relation. Where, of course, FA, what is FA? Well, FA is the unique C-linear map that has A as associated matrix with respect to the ordered basis B. So this is the relation between them. And then just using just this relation, one can perform a computation and show that the composition of the Möbius transformations associated to two matrices is equal to the Möbius transformation associated to the product of the matrices. And it becomes a straightforward computation that boils down to the item in exercise 11 that states that this composition of Möbius transformations of P1 is equal to this Möbius transformation of P1 associated to the composition of the original linear maps, which I remind you that it actually that this equality, that this is equal to this, it actually all came down to the very definition of composition of functions. So it came down to a very basic fact. Okay, and then one also uses in the steps in the computation process that allows you to see that this composition of Möbius transformations is equal to this Möbius transformation. You also use one of the fundamental theorems of linear algebra that states that if you are given two linear maps and you want to compute its matrix in terms of the matrices associated to the given linear maps, you actually have this equality that the matrix associated to the composition is equal to the product of the matrices associated to the linear maps. And so in this case, given that the linear maps have B and A as associated matrices, well, we see that this is equal to BA, and this allows us to verify that the Möbius transformation of this linear map is equal to the Möbius transformation of this linear map, simply because this linear map is equal to this linear map because of this. Okay, so the thing is, this computation, not this computation, the fact that this composition is equal to this, then boils down to the definition of composition of functions and this fundamental theorem of linear algebra, that the matrix of a composition is the product of the matrices. Okay, so and then knowing this, one very easily deduces that the Möbius transformations of C bar is indeed a subgroup of the group of cell homeomorphisms of C bar. A group that, by the way, we are going to denote in the same fashion as with P1 by mob plus of C bar. Okay, now along the way, what we have done is we have established a commutative diagram for each chosen basis B of C square, namely the commutative diagram that, on the one hand, to each bijective C linear map of this vector space associates the corresponding Möbius transformation of P1C, so to each F associates its shadow. On the other hand, the group homomorphism that to each invertible 2 by 2 matrix with the complex entries associates its Möbius transformation of C bar. That kind of these are kind of the associations so far of assigning to something a Möbius transformation. But we also have the passage, you know, that using the basis to each linear map, we associate its matrix, and you know we pull the formula. We pull the explicit formula we found for Möbius transformations of P1 using B to the famous formula of Möbius transformation of C bar. So what we did, let me see, what we did here. Oops, I'm so sorry. What we did here. Okay, in the previous class. Okay, right. Now, two exercises. One is that remember that C bar is a Riemann surface, right? And something sort of, well, I don't know if funny, but it turns out that Möbius transformations are precisely the biholomorphisms of this Riemann surface. So, show it. Okay, and then and then the next question is this. Okay, P1C. P1C, we know that it has the analytic topology with which we choose to work during this course, but it also has some other topology, namely the Zariski topology, or actually it has the structure of a projective algebraic variety. And this exercise is whether you can show that when we see P1C as a projective algebraic variety, the group of Möbius transformations is actually its group of automorphisms as an algebraic variety. So that's the question. Can you prove that? Okay. Now we have our for each given basis we have a commutative diagram. Notice that there's something funny going on. The vertical maps of the diagram, they both depend on having the basis, right? I mean, if we don't choose a basis, then we don't have the vertical maps. Okay, but still, even if we don't pick a basis, we still have the horizontal maps. Okay, which is something good to know, right? I mean, our homomorphisms are base independent. Basis independent. Okay, now, of course, when one has a group homomorphism, one of the first questions is, what is its kernel, right? Can we compute the kernel easily? And well, it turns out that yes, and then that if actually in either of these, the kernel consists of the non-zero complex multiples of the identity. So in other words, here it would be all the linear maps of the form lambda times the identity with lambda a non-zero complex number, and same thing here. The matrices of the form lambda times the identity matrix for lambda non-zero complex number. Okay, so the proof is actually quite easy. First of all, because of the commutativity of this diagram, and the fact that these are actually isomorphisms, that the vertical maps are isomorphisms, are group isomorphisms. from that, we see that it suffices to show to prove the statement for this homomorphism. That is that for any given matrix, its associated Möbius transformation is the identity if and only if the matrix itself is lambda times the identity for some non-zero lambda. Now, this direction is obvious. Think about it, right? I mean, because you have lambda alpha plus lambda z plus 0 divided by 0 z plus lambda, which is z, right? So this direction is obvious. Now for the other direction, we'll take any matrix and assume only that its associated Möbius transformation is the identity. We want to show that beta is 0, gamma is 0, and that this is a diagonal matrix, so that alpha is equal to delta. And the way we do it is by doing something which becomes one of the standard tricks in the theory of Möbius transformations, namely evaluating some points where you have a lot of control of what's going on. So first of all, since we have that this is the identity, well, mu of 0 is 0, but mu of 0 is beta divided by delta, right? And with this we automatically see that delta cannot be 0. Otherwise, if this were 0, well, first of all, delta cannot be 0 because the matrix is invertible, and then in that case this would be infinity. But then we would not have this, right? This equality that mu of 0 is 0. So delta is not 0, and then the next consideration is that then this division is just a division of two complex numbers with non-zero denominator. Well, this one has to be 0. So beta is 0, so we managed to do that. Second, now we evaluate at infinity. We know that evaluating at infinity gives me alpha divided by gamma, and then we see that this forces gamma to be 0. Otherwise, we would have just the quotient of two complex numbers where the denominator would not be 0, and then this would be a complex number, but then we would not have this equality. Okay, so now we know gamma is 0. And finally, we evaluate at 1, because at 1 we have this formula, but then these are already gone, beta and gamma. So alpha is equal to delta. And alpha being equal to delta and beta and gamma being equal to 0, well, we see that A is lambda times the identity matrix for some non-zero lambda. Non-zero because otherwise A would be the zero matrix, right? And then of course it would not be invertible. Okay, now notice we didn't use this in its full power. That is, we didn't use that mu A of any complex number is that same complex number. We didn't use it. We only used 3 points. We only used 3 points. So in other words, we actually proved something stronger. We proved here something stronger. We proved that if we have a matrix whose Möbius transformation fixes 0, fixes infinity, and fixes 1, then the Möbius transformation, then the matrix is lambda times the identity. So you see, we kind of as a parenthesis, we are actually showing that if a matrix, if we have a matrix and its associated Möbius transformation fixes 0, fixes infinity, and fixes 1, then the matrix is a multiple of the identity matrix, hence, its Möbius transformation is the identity. So we are actually proving if a Möbius transformation fixes 0, fixes infinity, and fixes 1, then it is the identity Möbius transformation. Okay, so this is sort of a parenthesis of something that will be useful later on, but in the meantime, we have finished the proof of our theorem. Okay, so well, of course, knowing that the kernel of this group homomorphism is the non-zero scalars of the identity, we see then let's say by the first isomorphism theorem for groups that that two matrices give me the same Möbius transformation if and only if one is a non-zero multiple of the other. So this means that we have established great amount of control over the assignment A goes to mu A, because we know in very concrete terms when it happens that two matrices give you the same Möbius transformation. Very concrete terms and with a very easy to verify condition, right? I mean, if they give me two matrices, it is very easy to check whether one is multiple of the other or not. Okay. Okay, and then the next is that well, for each ordered basis of C square, we can associate to each linear map its matrix with respect to the basis B, right? And then we can associate to each Möbius transformation of P1C the Möbius transformation of C bar induced by the matrix representing the linear map, right? Okay, or if you want representing the Möbius transformation. Okay, so my point here is that for this corollary, again, the ordered basis is used only to pass, in these vertical isomorphisms, but not informing the rows. So the rows, by definition, every Möbius transformation is associated to a linear map. Is the shadow of a linear map. So of course, the function that to each linear transformation, to each bijective linear transformation associates its shadow is surjective, right? Everything is shadow of something. Same thing here, right? By definition, a Möbius transformation is the function associated into an invertible matrix. So the map that to each matrix associates its Möbius transformation is of course surjective by definition of what Möbius transformation is. And what we've done in the previous theorem, which you can see here on the left, is to compute the kernel of this map and the kernel of this map. Notice this is the this square is this square. Okay, so we computed the kernels. The kernels are these ones, non-zero multiples of the identity in each case. Okay, so we have that commutative diagram with those exact rows because we computed these ones as the kernels of these ones, right? Okay, so what? Well, this means that these kind of mysterious groups can be computed in concrete terms, because they are both isomorphic to this quotient, right? Which I would say it looks very concrete. right? It looks very concrete. And it's denoted PGL2C, the projective general linear group. Okay, so that's one thing. Now, next consideration. Well, of course, there is a very natural question. So we know that different Möbius transformation, that different matrices can give you the same Möbius transformation. We know that, right? I mean, it's this corollary. This corollary. We know that. Okay. So this gives us this opens the door to the question. Okay, is it possible to represent any Möbius transformation using a matrix of determinant 1, right? I mean, right? I mean, can we focus our attention in a group that is not necessarily the whole GL2C, but maybe a smaller group, and still get all possible Möbius transformations of C bar? And the answer is yes. The answer is yes because we know that determinant is multilinear, right? I mean, so that let's say that the determinant of let's say lambda alpha lambda beta gamma delta is equal to lambda, the determinant of alpha beta gamma delta, and similarly for the other row. Which means just divide any matrix by the square root of its determinant, or I would say by any of the two square roots of its determinant. So really we have two roots to choose from. Yeah, divide the whole matrix, right? I mean, and we need the square root because with each row a scalar comes out from the determinant. So we need the square root so that it's square root and then square root, so it gives you the determinant. Right? Okay. And then we need to divide by the whole alpha because of the corollary, right? I mean, sorry, we need alpha to be divided by one single scalar, so both rows by the same scalar, because of this. Right? Okay. Anyway, so it is possible to represent any Möbius transformation with a to present any Möbius transformation as the Möbius transformation associated to a matrix of determinant 1. Okay. Okay. So this means let me then go onto that version onto the SL version of this GL diagram. Okay. Namely, what I've just did here is to show that if I restrict this homomorphism to SL2C, where SL2C is the group of matrices with complex entries and determinant 1. That is, again, here to any matrix I associate its Möbius transformation. What I see is that this is still surjective, right? So what this paragraph says is that this one is surjective. Right? Now, what is its kernel, right? What is its kernel? Well, I still know that any matrix, but now in SL2C, goes to the identity if and only if it's a non-zero multiple of the identity matrix, right? So it's the kernel of this one should be the non-zero scalars of the identity that still have determinant 1. But you see, but then lambda square has to be 1 because that's the determinant of the diagonal matrix lambda 0 0 lambda. So it's just plus minus. Okay, and then using any ordered basis B, we have this commutative diagram with these exact rows. Where here, here I would be defining SLZ of C square to be the group of matrices, sorry, the group of linear maps, of C linear maps of C square that have determinant 1. Right? Where, how do I compute the determinant? Well, with any matrix representing it. Right? And we know that this is a well-defined, you know, that associating to each linear map its determinant with respect to any basis is well-defined and does not depend on the basis used, on which basis is used. Okay, and from here we see that that this group is isomorphic. Well, both of them are isomorphic to this quotient, which is even somehow simpler or easier to deal with than this one, because here you see, because here the kernel is very small. I mean, the group by which we mod out is very small, right? So this tells me you know, these ones are almost SL2C. That's what it tells me. Okay, and this is a PSL2C, the projective special linear group of C, which here as a byproduct, of course, we are asserting that these two are isomorphic. Okay. So far for the group structure. Okay, so we did say a few things, a few new things, other than the expected, you know, pulling the group structure of this one to group structure of this one, namely this. We did some other things that I think are quite interesting. So, okay, so let us discuss a little bit about the transitivity. So of course, when you have a group, the action of a group on a set or a space, one of the natural questions is this action transitive, right? And if so, to which extent, right? If so, for instance, how large are the stabilizers, for example? Another words of saying to which extent is okay. So if it's transitive, how much of the behavior can I impose? In other words, okay, if it's, you know, if I know that given any 2 points, if given any 2 points, there's always one element taking one to the other, that is being transitive. I can say, okay, now how about taking also a second point and a second point? Is it can I ensure that the element that takes the first to the first can be chosen in such a way that also takes the second one I want to the second one I want? Yes or no? Right? And if yes, then third, blah blah blah. Right? I mean, so one can, when one has an action, one can ask whether the action is transitive and say, okay, and if so, to which extent, in both senses, right? In saying, okay, how large are the stabilizers, or how much transitivity do I have in many points, right? And then for C bar, the answer becomes 3, right? I mean, that is, if you give me 2 triples of elements of C bar, satisfying, each triple satisfying that the 3 elements are distinct. The 3 elements are distinct. Although some of these are allowed or is allowed to appear here, right? So in each triple, I do not have repetitions. So in this one, I do not have repetitions. In this one, I do not have repetitions. But I allow that maybe some of these 3 points are equal or is equal to some of these 3 points. Okay. Why different? Well, because in what I was saying, like if one has transitivity in sending any point to any point, and then you want to ask, okay, whether you can add a second point. Of course, the second points, you take them not to be the original ones, right? Because for the original ones, you already know the past. In the case of transitivity, you already know that there exists such, right? So for the second one, you don't want to put the first one, right? Or you don't want to do like this and this, because then in that case you are not really asking the correct question. Okay, anyway, if you give me 2 of these triples that I said of elements of C bar, in each of which I don't have repetitions, although it's possible that some of this appears also here. Okay, then there exists exactly one Möbius transformation sending this triple to this triple, this order triple to this order triple. So the first element to the first element, the second element to the second element, and the third element to the third element. Right? So I take the triples ordered. And of course, if you permute this, then the question changes. And then there may be some other, then maybe you have to change the Möbius transformation you take. But if you give me the 2 order triples, I mean, because you gave me, okay, I want this one to this one, and the second one to the second one, and the third one to the third one, because your original question was, to which extent do you have transitivity? Then there exists exactly one. So that's what the famous theorem on transitivity of the action on triples of distinct points asserts. Now, for the proof, notice that proving the theorem, namely that there exists exactly one, so both existence and uniqueness, follows, both of them, both properties, existence and uniqueness, follow if we can establish existence and uniqueness in one special case, namely where you want to send the first one to 0, the second one to 1, and the third one to infinity. Existence, why? Because if you show it for every triple, for every order triple of distinct points, W1, W2, W3, then you can always pass through this triple, right? I mean, in other words, send this to this, this to this, this to this, and then take the inverse of the one that sends to your other points. Right? That's for existence. And for uniqueness, once we know uniqueness in this case, where we in this special case, then we have uniqueness in general, because otherwise, if there were 2 Möbius transformations with the desired behavior, then you can compose one with the inverse of the other, and then you would have 2 Möbius transformations that send this to 0, 1, and infinity. Right? Okay, so the theorem follows from proving a special version of the theorem, both in existence and uniqueness, and the special version is when the target triple is this very specific ordered triple. Now, of course, I mean, these are, of course, sorry, W1, W2, and W3 are, of course, supposed to be different. This means that at most one of them is infinity. So this means that you see, at most one of them is infinity. So this means that the generic case, generically, the 3 of them are not infinity. In other words, having one of them being infinity is like a super special case. Right? In any case, so in this generic case where the three of them are actually complex numbers, then we see, okay, I mean, so somehow one has this formula, but the important thing is how to arrive to that formula, right? And the point is, we want W3 to land in infinity, right? So what's the best way to make that happen? Well, it's divide by Z minus W3, and of course, you can say, okay, divide by this, square or whatever also does work, sure. But we also keep in mind that we want a Möbius transformation. So we don't forget that we want something of degree 1 divided by something of degree 1 in Z. Okay, so that's how we start. We put that there. And then we say, okay, but we also want Z1 to land in 0. Sorry, W1 to land in 0. Okay, then put it in the numerator. Okay. And then you say, okay, but how about W2? You want W2 to land in 1. Okay, well, and then you say, okay, so far I have this formula. Plug in W2 and see what happens. Then you obtain this number. But you want 1, you don't want this number. Okay, so just divide by it, right? Divide by it. In other words, multiply by its inverse. And then and then consider that rule of correspondence. This rule of correspondence, by construction, has the behavior you have, the behavior you want. Okay, but is it the Möbius transformation associated to something? Well, the fact that we have degree 1 in Z divided by degree 1 in Z says yes, it is, right? And then it's quite easy to see that actually, if we consider this matrix, then its associated Möbius transformation is the one we just produced. Okay. Now this is if none of the points W's, if W1, W2, and W3, if neither of them is infinity. Okay. And then the next exercise is that I leave you is what happens if infinity is one of the three. And here, I'm sorry, but you are going to have to consider 3 cases because W1 equal to infinity tells you infinity has to go to 0, but W2 equal to infinity tells you W2 has to go to 1. W3 equal to infinity tells you infinity has to be a fixed point. So somehow there's no way around it. You are going to have to consider 3 cases. They are very simple. And the hint is just follow my advice, right? And then, well, just follow the same trick, right? Remembering that that it is allowed for alpha to be 0, in which case you have polynomial of degree 0 divided by polynomial of degree 1, or gamma is allowed to be 0, in which case you have polynomial of degree 1 divided by polynomial of degree 0. So there's you have certain freedom in the degrees of those two of the polynomial in the numerator and the polynomial in the denominator of the expression of the Möbius transformation. Okay. Right, so that's as far as it goes regarding existence. Now, how about uniqueness? Uniqueness of I'm still in this case. Okay. Now, so for uniqueness, we apply something that I said a few moments ago. That actually one can prove that if we have a Möbius transformation that fixes 0, fixes 1, and fixes infinity, then that Möbius transformation automatically is the identity. And the proof is the same. We actually already gave it in the other argument. Right? I mean, so because yeah. So suppose it's clear, right? I mean, it's clear that if we show that the identity is the only Möbius transformation that fixes 0, 1, and infinity, then this nu that we computed is the only one that sends this W1, W2, and W3 to these guys, right? Why? Again, because then take two of them and compute one with the inverse of the other. and you know that that one with the inverse of the other fixes 0, fixes 1, and fixes infinity, so it's the identity. So the two Möbius transformations nus with the given behavior are the same. So it is clear that it suffices to show this. So somehow, yeah. Okay, so, but you see, it's the same computation, right? Because now we are in the very same three situations, and in those three situations we know how to do the trick in the coefficients, and this implies that that the matrix A is a multiple of the identity, but this means that the Möbius transformation itself is the identity. Okay, so the theorem follows. Right, so summary of the theorem. So first of all, the existence and uniqueness follow by establishing the very same theorem, the very same existence and uniqueness, but in this special case where one has 0, 1, and infinity. Okay, in that case, existence is quite easy. I mean, one just analyzes the behavior one wants to know what to put in the numerators and denominators. And second, for the uniqueness of nu in this special case, one sees that by composing with one with the inverse of the other, it suffices to show that any Möbius transformation fixing 0, 1, and infinity is necessarily the identity. So the thing is, don't get confused. The Möbius transformation, this one is not supposed to be nu. This one is supposed to be the composition, let's say, of nu inverse with another Möbius transformation that also sends W1, W2, and W3 to 0, 1, infinity, respectively. Okay. So that's the summary. I would say quite elegant. And you see the corollary is that, well, since now we know that given any two triples of distinct points, there is exactly one Möbius transformation sending one to the other, and since we know that whenever you give me a triple of distinct points, there is always one Möbius transformation sending the first one to the first one, the second one to the second one, and the third one to the third one, namely the identity. We see that any Möbius transformation that fixes any 3 points, now not necessarily these ones, but any 3 points, is the identity. That is, if you give me a Möbius transformation, and this Möbius transformation is not the identity, then it has at most 2 fixed points. Right? Okay. Something that is very, very, very useful. That is very useful, and that will help us in the long run to. It's one of the conceptual reasons that will help us in the long run to reduce the study of the geometric behavior of arbitrary Möbius transformations to the study we already made in the case of the standard examples. This, that there are at most 2 fixed points for the non-identity Möbius transformations. Okay, now, so you see, we've seen that in this special case of the theorem, we have actually like an explicit matrix, and here also in the exercise I want you to find an explicit matrix whose associated Möbius transformation has the desired behavior. Right? So in other words, we see that it is possible to perform explicit computations. As such, I would like you to write down an algorithm, or even better, a program, let's say a Python program, that takes these 2 triples and as an input of the algorithm, and as a result, it gives you a matrix with the desired property. Right now, to be consistent with here, maybe here I should write here the other way around. Yeah, and maybe even here I should just, oops, well, that will be just a waste of time, but. Okay. Okay, so now we know that there is the action of the group of Möbius transformations mod plus of C bar on the set of triples of distinct points of C bar is simply transitive. It is transitive because there is always one Möbius transformation taking one order triple to the other, and it's simple because there's exactly one. Okay. Now the next thing to show that under Möbius transformations, circles always go to circles. As I said, it is a fun game to try to deduce this, to deduce that the image of any circle in C bar under any Möbius transformation is again a circle in C bar from the simple transitivity in triples that we just proved. It is a fun game that I think is very instructive to play, even if you reach nowhere, even if you don't get anywhere with it. But I think it gives you playing the game, trying to prove it, that prove this, doing that. Gives you a lot of intuition of what is true and what happens and what does not happen under Möbius transformations. Okay, now why would it occur to me that that circles go to circles under Möbius transformations, right? I mean, what is the moment where I conjecture that any Möbius transformation sends circles in C bar to circles in C bar? I would say that the moment where one conjectures that is when one sees the standard examples, because in them, it is just obvious, right? It is obvious that translations send circles to circles. It is obvious that that homotheties send circles to circles. Now, circles now not necessarily centered at the origin, right? So the origin here, and we know that circles there go to circles also centered at the origin. But if it's not centered at the origin, yeah, but it's still a circle. Rotations, what can I say? And loxodromies, well, any loxodromy being the composition of a homothety with a rotation, it follows. Okay, and then one says, okay, can we prove it in general? The answer is yes. And I'm going to need an auxiliary fact, namely that certain specific Möbius transformation sends circles in C bar to circles in C bar, namely the Möbius transformation that sends Z to 1 over Z. Now the fact that this Möbius transformation sends circles to circles can be proved in two different ways. One is using synthetic geometry and using similarity of triangles. Right? I mean, yeah. One recurs to a picture that looks like how is it? Yeah. Right now I don't quite remember. I would have to think a bit more. Okay, but the other proof, recurs to the fact that we already know that that the stereographic projections send circles to circles, circles in the sphere to circles in C bar, and vice versa. Now, there is one parenthesis I want to make. recall that the way we proved that the stereographic projections send circles to circles was in two cases, what was performed in two steps, in two cases. In the first case, we covered the circles on the sphere that pass through the North Pole, through the projecting point, and the circles in C bar of the form straight line union infinity. And for them, the argument was geometric and was that was pretty much it followed pretty much from the basic observation that if you have a plane in R3 that passes through the North Pole, then the stereographic projection related to the circle of intersection, it all happens inside that plane. So the image has to be this straight line union infinity, right? And vice versa. Yeah? If you have a line, then you just take the unique plane that passes through the line and infinite and the North Pole, and then you notice that everything happens inside the projection of for this line. Everything happens inside that plane. That was the first one. And for the second one, for the second case, which were the circles not passing through the North Pole and the circles in C, so the circles that are actual circles in the complex plane, our argument was just a basic, very basic algebra, right? So algebraic manipulations. In particular, we did not use in either of these two arguments, we did not recur to inversion. So to inversion with respect to spheres. Okay, so why do I say this? I say this because if we had, then there would be a danger of circular argument, of saying the stereographic projections send circles to circles using some argument involving inversion. And now we are going to show that this one sends circles to circles, you know, yeah, that these certain inversions send circles to circles, using that we know that this sends circles to circles. You know, it would be like we know this because of inversion, and for inversion we know it because of this, and that would be there would be a danger there of circular argument. But that is why we did not show this using inversion, but rather a direct geometric argument for certain types of circles and very basic algebraic manipulations for other types of circles. So this one we used it without recurring to any inversion whatsoever. Okay, anyway, so let's prove this lemma. Now we know that stereographic projections send circles to circles using this argument, this plane argument and this basic algebraic manipulation argument. Okay, fair enough. Now, this one for which you want to prove that sends circles to circles, well, you see, this one is equal to here P inverse, right? To this expression, where here you have P inverse and then mu 110 P. So, and you know that this one sends circles to circles and this one as well. So if you manage to prove that this one sends circles to circles, you are done. And that's what we do. Now, why does it send circles to circles? I mean, you see, it is quite easy to see that this one, you know, first first projecting to C bar and then applying this 1 over z and then coming back to the sphere is actually the rotation around the x-axis. So for instance, so here you have C bar, right? Well, the point at infinity is far away. And then, for instance, consider only C bar, right? So forget about the sphere that you are seeing there, and think for the moment only about C bar. So this line, this segment, this ray departing from in this case it would be -1 if this one is a negative x-axis. This one, when you apply 1 over z, you go here in this direction, right? Same thing with this blue this greater than 1 ray. When you apply 1 over z, you get this in this direction. Okay. Something similar for in the y-axis greater than 1. And the y-axis less than -1. Okay. Now, under the stereographic projection, this segment of circle in the zx axis is mapped to the greater than 1 part. Similarly here, this segment of circle in the xz axis corresponds to this one. This segment, this segment of circle again in the xz axis goes to this one, right? Because it's and similarly with these ones. Okay, and now think of this. Like think of this, how in C bar, how this ray goes to this ray, right? But now compose it with conjugated with the stereographic projection. So this one goes to this one, which under 1 over z goes to this one, which under the stereographic projection goes to this one, right? So the image of this one under this composition is this one, like this. Similarly, this one, right? I mean, this one under 1 over z goes to this one, but okay, but now this one here under stereographic projection goes to this one here, under 1 over z goes to this one here, under stereographic projection goes to this one here. So the image of this one under this composition is this one. So at least we have this correspondence, but it's not hard to see in the remaining cases. I mean, not in the remaining cases, for more general rays and segments of circle, right? And remembering that let's say if you have, let's say, a ray here in C bar, right? So let's say it's a ray in C bar, so it leaves the unit disk here. So the unit disk, and then you have your ray. So when I step here, I'm in norm greater than 1, and then 1 over z is inside, but with norm smaller than 1, right? And so you see this, the fact that this kind of on the other side somehow, I mean on the other side of the y-axis, of the x-axis. That 1 over z is on the other side of the x-axis. That's what amounts to for the rotation of 180 degrees, right? So think about it, and it's actually I would say fairly easy to see. Okay, but being a rotation, this one being a rotation, obviously maps circles on the sphere to circles on the sphere. Right? Hence, this one as well. Okay. So here I have to say that I learned this argument from Emmanuel Gonzalez Celio, who took this class with me 1 year ago. Because I always used to give the geometric argument here using a similarity of triangles, right? Some synthetic Greek geometry. Okay. Right. And now, well, now we know that this very special, very specific Möbius transformation sends circles to circles. Okay. And now we are going to use that to show that every Möbius transformation of C bar sends circles of C bar to circles of C bar. And of course, we know not only that this one sends circles to circles, but that all the standard examples send circles to circles. And the strategy to prove this theorem is to show that every Möbius transformation can be written as composition of the standard examples and this slightly less standard example. Okay, so take any invertible matrix with complex entries, and then two cases: gamma is 0 or gamma is not 0. If it's 0, then it's quite easy. It's quite easy because then the Möbius transformation is the composition of a homothéty with a translation, and both of them obviously send circles to circles. Okay, now for the second case, so it's a little bit of computational trickery. So take this expression, and then I mean somehow let's say if you want, one of the tricks is to try to make the determinant appear. So here we have beta. Let's multiply with gamma. But then then we really multiply all of this with gamma and all of this with gamma to maintain the equality. And once we multiplied with gamma both numerator and denominator, we add a 0, namely the part of the determinant of A that is still missing. So we add this 0. Okay, so notice that the determinant, how does it appear? It appears here, and it's actually minus the determinant of A. Okay, so once we have that, so somehow somehow if you want kind of the key point is make the determinant of A appear. All right. Why make it appear this way? I would not be able to explain like how does it occur? Would it occur to me? I mean, really, what I'm doing is just following Anderson's book. So here I would not be able to say more than that of how you can come up with what needs to be done. But okay. So now once we are here, then see here we have gamma z plus delta, and here with alpha, with alpha here, we have also gamma z plus delta, right? So the gamma z plus delta can be cancelled, right? And then we are left only with alpha divided by gamma. So all of this becomes alpha divided by gamma. Then plus this, which we separate into, the kind of the part that has only the only scalars, and the part that involves z, which would be 1 divided by gamma z plus delta. Okay, so once we did that, we notice that, for instance, that what is the process we are following? I mean, that in order to obtain
in order to obtain mu of z from z, what do we do? Well, first we multiply z with gamma and add delta. So that's the first thing we do, which we know sends circles to circles. Then after that, we invert, right? Because we take the result, which is gamma z plus delta, and we invert it. So to the result we apply this one, which we know by the lemma. We know by the lemma it sends circles to circles, and that's the most delicate point at this moment, because then later we multiply by a non-zero scalar, which we know sends circles to circles, and finally the result is translated, and translation sends circles to circles. So the result follows.
Okay, so let us now show that any Möbius transformation takes disks in C bar to disks in C bar. That is that the image of any disk is a disk. Okay, so take your Möbius transformation. That Möbius transformation is a self-homeomorphism of C bar, and take a circle. So the complement of this circle in C bar has two connected components, which are precisely what we call disks, right? I mean, by definition, a disk in C bar was or is a connected component of the complement in C bar of a circle in C bar. Right? Okay, so take your circle in C bar, take its complement. The thing is, the circle splits the complement into two connected components, right? So take one of the two connected components, then since our Möbius transformation is continuous, its image is contained in one of the two connected components of the complement in C bar of the image of the circle we had taken originally. Okay, so at least it's sitting in one of the two disks determined by the image of the circle. But then it has to be the whole thing, the whole connected component, because otherwise otherwise there would be something in the other connected component that has to go there, but then it's both connected components that are mapped into the same component. Then there's no way for the other connected component to be in the image, right? So so the image of this connected component is contained in the connected component by continuity, and then by the same continuity it has to be the whole thing, and because of bijectivity, right? Why? Because otherwise there would be a point in that connected component that does not come from this one. Then that one would have to come either from the circle, but this is not the case. It has to come from the other component, but then the other component is mapped entirely into this component. So the image of the two connected components is completely contained in one of them. So the other one does not belong to the image. So the Möbius transformation is not surjective. Okay, so this is an easy corollary. Just follows from easily from continuity. But now maybe more interesting than that is the following. Take your two triples of distinct points in C bar as before. Then now we know that there is a unique Möbius transformation taking these three in order to these three. So first one to first one, second one to second one, third one to third one. Okay, and now consider the circle determined by this 3 and the circle determined by this 3. Since circles are sent to circles, well, it must be the case that the circle determined by this 3 is mapped by this Möbius transformation to the circle passing through this 3. Right? Okay, so this means that if I take one of the disks determined by this circle, this one goes to one of the two disks determined by this other 3, by the circle. Right? Okay, which one of the two? Right? You can say, yeah, okay, so you can determine that very easily. I mean, take a point in the interior of the circle and then see where it lands, and there you have your disk, right? There you have which one of the two. Sure, but I would like to have the answer purely in terms of only the two given triples, right? Without having to say, okay, take someone in the interior. Just by looking at how the two triples are configured in C bar, just from that, no, okay, this disk has to go to this disk and this other one to this other one. Okay, so let's do that analysis. Let me do the analysis in the case of known of the points W1, W2, W3, and none of the points Z1, Z2, Z3 being an infinity, and even stronger, that the circles determined by them are both circles in C and not circles of the form straight line union infinity. So for this analysis that I'm going to make, for these considerations, let me assume that W1, W2, W3 are 3 points in C that are not Euclideanly collinear, and that Z1, Z2, Z3 are also 3 Euclideanly non-collinear complex numbers. Okay, so that we indeed have such pictures. Okay, now, so you see here, when we ask ourselves, along the circle determined by W1, W2, and W3, I mean, traverse that circle in order, right? I mean, traverse that circle in such a way that you pass through the points W1, W2, and W3 in order, right? So for instance, in this case, we would have to traverse the circle in this direction in order to pass through the 3 points in order, whereas in this other situation, we would have to traverse the circle in this direction in order to pass through the 3 points in order. Okay. Regardless, orient the circle that way, and when you orient the circle that way, and you traverse the circle, then exactly one of the two disks determined by the circle is somehow bounded clockwisely, and exactly one counterclockwise. For instance, if in this case, if I traverse the circle as I said in order with respect to W1, W2, W3, then this disk somehow is immediately oriented clockwisely, and the other disk is immediately oriented counterclockwise. And while here, if in this other situation I traverse the disk as I said, in order with respect to W1, W2, and W3, notice that this disk is then oriented counterclockwise, and this one the rest is oriented clockwise. Right? This is easier to see in the sphere, right? So for instance here, if this one W1, W2, W3, then I would have to traverse the disk this way, right? And then this disk would become the one traversed clockwise, and this other disk the one traversed counterclockwise, right? This disk, so let me, maybe this looks nicer. Okay, whereas if this is W1, W2, W3, for instance, then I would have to traverse the circle this way, and then this disk then becomes oriented counterclockwise, and this other disk becomes oriented clockwise. Okay, so now you know what I'm trying to say. Okay, and then what must happen that like for instance in this case where the orientation of the disk is clockwise, and I look at the images of these three, which are Z1, Z2, Z3. Let's say here Z1, Z1, Z. Let's say Z2. Oops. Let's say Z2 here. Yeah, there's no problem. Z1, Z2, Z3. Well, what should be the image of this disk? Of course, it has to be the disk that, when I do the same for this circle, is oriented clockwise. Okay, so if instead of that I have, if instead of that now I have Z1, let's say that now Z2 is here and Z3 here, then the image of this circle, of this disk, sorry, which is oriented in the clockwise fashion, now it cannot be this, right? So it has to be the outer one, right? Why, right? Why? In reality, the real reason is, in the end, that Möbius transformations preserve the orientation, are orientation preserving. So this is why in this case the image of this one in this second case has to be this outer one, while in this other case, where instead of this we had this, the image of this disk has to be this one, right? In this case, right. In the end, it all boils down that at around any point here, the clockwise orientation must be mapped to the clockwise orientation around here, right? Like locally, let's say. But then when one connects this, one sees that in this one traverses, one cuts in order, three crosses in order, and then that same order has to be, that order has to be the same in both of them, right? So in the end, it really comes down to the fact that Möbius transformations are orientation preserving, right? So remember, what is orientation preserving? Well, positive determinant, right? Yeah. I mean, we give an orientation to every point in C bar, to C bar, and then we know what it means, positive and negative determinant. Right? Okay. Okay. So now I think that's more or less it. What I wanted to say. But so you see here. I mean, I did solve the question I had, right? I mean, if I just by looking at Z1, Z2, Z3, at W1, W2, W3, and Z1, Z2, Z3, just by looking at them, I know each disk determined by the circle passing through the 3 here, where it go to which disk it goes, right? So. Okay, and everything boils down to just kind of to just how they are combinatorially configured, how the two triples are combinatorially configured. Okay, so let's do some summary of today's class. So first, I started recalling that P1C is a subgroup of the group of self-homeomorphisms of P1C, which we had proved very easily already earlier. Then I explicitly showed the computation that allows us to see that this implies that the Möbius transformations of C bar form a subgroup as well, but now of the group of self-homeomorphisms of C bar. I emphasized that our proof that composition of Möbius transformations is Möbius transformation comes down to just the definition of composition of functions and to this fundamental theorem of linear algebra. Then we saw that we have for each ordered basis a commutative diagram that relates the Möbius transformations of P1C with the Möbius transformations of C bar. We computed the kernel of the two homomorphisms that to each linear map associates the Möbius transformation and to each matrix associates its Möbius transformation. The kernel turned out to be kind of easy to find, or easy to find, and it's just the non-zero complex multiples of the identity. That is, it turned out to be what we expected, because it's quite clear that the non-zero multiples of the identity give you the identity Möbius transformation. So it turned out the kernel turned out to be exactly nothing worse than the expected, right? I mean, actually the expected. Okay, this in particular helps us to decide in practical terms when two given matrices give me the same Möbius transformation or not by just by looking at their entries. We also went into a little bit more of sophisticated language, and so that somehow what it turns out is that the group of Möbius transformations of P1 or of C bar, they are both isomorphic to this projective linear special linear group, and we, where you mod out only by plus minus the identity, which somehow tell us that these ones look very like this group, and you only have to be careful with multiplying matrices by -1 sometimes. Okay, then we went on to prove the simple transitivity on triples, this famous property of Möbius transformations. Okay. Somehow our proof somehow allows us to extract, well, our proof, and also the part of the proof that is left to you, allows us to write down an explicit algorithm to produce the Möbius transformation, to produce for each pair of triples of distinct elements of Z bar the corresponding Möbius transformation explicitly. Right. So somehow this is a proof that can be exploited in explicit computations. Okay. Another consequence of this, one consequence of simple transitivity is the fact that any non-identity Möbius transformation has at most two fixed points, and this is one of the facts that are going to allow us to transport the analysis of the geometry we made for the standard examples to arbitrary Möbius transformations. So this corollary turns out to be very, very important. Well, of course, there's one little point missing in this corollary, and is whether you have at least one fixed point. The answer will be yes. We will see that in the next class. And then to close to finish today's class, we saw that every Möbius transformation sends circles to circles in C bar to circles in C bar. More pedantically, if you want, that the image of any circle in C bar under a Möbius transformation is again a circle in C bar. And we did it by recalling that our standard examples, they all obviously sent circles to circles, and then this, let's say, almost standard example also sends circles to circles by an argument that I find rather beautiful, because it moves to another model where it turns out to be very easy to see that it sends circles to circles. As an exercise, I left you to try to deduce this property, that is this theorem, try to deduce it from the simple transitivity in triples. Yeah, it's a fun exercise, a fun game. Okay, as a consequence, just by topological consideration, one knows that hence, since we know that every Möbius transformation sends circles to circles, then it also has to send. Then, because of that, and because it's continuous and bijective, it must send disks to disks. And finally, we just described a general, one method, one way of explicitly deciding where a disk, what's the image of to know which disk in the codomain is the image of a disk in the domain, just by looking at the original two triples of distinct points, and the final answer depends on knowing that Möbius transformations preserve the orientation of C bar. And that's it for today.